Hello guys, welcome to our channel ECE TechNest. Today in day 5 of digital design course, we are going to study about types of Verilog coding and introduction to gate level modeling. Types of Verilog coding styles. Verilog allows you to describe hardware at different levels of abstraction. Think of it like building a house. You can describe the floor plan, the wiring, or where every single brick goes. We have 4 types: gate level, data flow, behavior, and switch level. The level of abstraction in gate level is very low, and in data flow it is medium, behavior it's very high, and in switch again it is very low. Gate level describes the design using primitive AND gate, OR gate, different type of gates. In data flow we use continuous assignment, assign, and other logical operators. Describes behavioral modeling describes a circuit on what it does. It uses typical C programming logic like if else and case statements. Switch level, it is very low. This is done using your MOS transistors. This is rarely used by logic designers. In most cases, RTL design engineers will be using behavioral description or else data flow description. Level of abstraction, you might be confused with what is level of abstraction. Level of abstraction refers to the degree of detail you provide with describing a digital system. We typically visualize this using the um, Gatsky-Kun chart, also known as a Y chart. But for a Verilog beginner, they're best understood by how much manual labor the designer does. So in behavioral description, it will be very high. In modern VLSI flow, you can usually write the code at the behavioral or data flow level. You then use a synthesis tool like a design compiler or a Viva to automatically convert your high level code into a gate level netlist. Introduction to gate level modeling. As you can see, we have named all of the gates. Gate level modeling is the closest representation to the actual hardware logic. You are essentially instantiating predefined basic logic gates that Verilog provides as built-in primitives. Verilog has several built-in gates ready for use, such as input gates. That there are multiple input gates, such as AND, NAND, OR, NOR, XOR, XNOR. These are all multiple input AND gates. And for single input gates, we have such as NOT and buffer. Because it has only one input and one output, it is called single input gate. The general syntax for writing a gate primitive is you will write the gate type. That is, for example, if you have an AND gate, you will write AND and how many times it is being called. If I am calling it for the first time, I'll write A1, AND of 1. And first you have to write the output pin, then your input and the next inputs. The important thing to note here is the output must always come first in the terminal list of these primitives. That means output always has to be first. Let's design a 2:1 mux. The logical expression you would be knowing. We have discussed this in our previous lectures. Based on the select line input, either we get input 1 as our output or input 2 as our output. This is the gate level description or the gate level diagram of a 2:1 multiplexer. See, this is the code for mux 2:1 using the gate level modeling. You have input A, B, and select line S and output Y. You also declared wires. Wires are net. We have discussed this in our day 2 or day 3 lecture. You can go and watch it out. You know why we use this wire here? When we want to connect between this to this, no, or this, I'll write this as NOT gate wire. It will connect the output of the NOT gate to this AND gate. This is where we'll be using the wire. See, here we have already done it, right? See, NOT of gate, S bar and S. So we know that S bar is the output and this is the input. AND gate, it is called second time. This is your, what do we call it? Instance name. G2 is your instance name and output 1. So if we are talking about this one, this gate, we have the input and we have a S bar and this is the AND gate, this G2. Then for G3, we are talking about input 2, select line is in normal condition, it is not the inverted one. So we get the output here. So output will be AND of out2. And the final will be the combination of these two. So we have declared it as a wire, right? So you'll know here. These two are wire AND out 1 and AND out 2. This 2 will be given as an input to the OR gate. See, it is given as an input to the OR gate, and this is the final output Y. This will come as your final output. Why to use gate level? You might be questioning. I have told in the beginning that behavioral and data level are the most used description. Then you might ask, why do we use gate level description? See, it has a structural accuracy, knowing exactly which gates are being used. In this design, you do actually are not knowing that what gate is being used. You are directly declaring this and you are writing the program. But in gate level, you'll always be using the gates, so it will be easy to understand. Post synthesis verification. If you are using gate level description, it is easy to check the netlist generated by tools to ensure it matches your intended logic. Performance. Here, what you can set is a precise gate delay modeling. See, you are putting a 2-unit delay. We'll also discuss about delay in our upcoming next lectures. In the next lecture, we'll be talking about data flow modeling, behavioral modeling, and switch level modeling. These are very important since the industry is more focused on data flow modeling and behavioral modeling. We'll be discussing that in depth. In the next lecture, we'll also be going through practical applications, such as we'll be working it on EDA Playground, and we'll show you how the waveform works. If you have any doubts, feel free to ask in the comment section. Thank you.